Well, thanks for having me. My talk is going to have some elements in common with both of the last two, actually. So I'm a climate scientist, and I'm going to be talking about sea level rise, and particularly the ice sheet and glacier melting part of sea level rise, and how we've used probabilistic machine learning to make predictions for the IPCC. So what is the IPCC? The Intergovernmental Panel on Climate Change. It's a big body that assesses the evidence on climate change, produces these huge reports about every 7 years or so. We're just about to start the new cycle of the next one. And this is a picture of the cover of the last one, the physical science part of it. And I was an author on the chapter on oceans, cryosphere, and sea level change. So this is a big sort of almost textbook of evidence on climate change, which brings together all of the literature and methods that we've got. And so at the start of that report, you've got a summary for policymakers, for sort of government representatives and the public, although it's a bit technical perhaps for many audiences. And within that, we've got sea level projections. So these are the projections to the year 2100, the graph starting at 1950. And we've got a few different curves here. So the beginning part is observed sea level rise. So this is the global average. It does change locally. And we've got, I'm going to not talk about the high dashed line. That's essentially a sort of expert elicitation. But the curves at the bottom there are for different emission scenarios. So it shows the median for 5 different emission scenarios, going from very low emissions in the future to very high, a sort of burn everything scenario. And then it's got uncertainty shading for a couple of the scenarios there. And it ranges from about 0.5 meter to 1 meter, which doesn't sound like maybe a lot, but that has very, very disproportionate effects on the extreme sea levels around the world, the risk of coastal flooding. They multiply very quickly with just tens of centimeters of sea level rise. And sea level rise has multiple components, so melting of glaciers and ice sheets are the sort of most famous part, but there's also a big component from the oceans warming and expanding, and also water sort of stored around the land running off into the ocean. And so I'm going to be focusing, as I say, on the land ice contribution. We've got different components of that around the world. We've got the 2 ice sheets at the polar regions, Greenland at the top and Antarctica at the bottom. And we've got the global glaciers, so mountain glaciers mostly, which are typically divided into 19 regions around the world. And these blobs are basically showing where those are, and the size of the circle is the how many, basically, the area of the glaciers. So this is what I'm focusing on, predicting the future under climate change of all of these sources of land ice for sea level rise. So the aim here is to estimate probability distributions for the sea level contributions from all of these land ice sources this century, so from 2015 to 2100, under any emission scenario, any climate scenario. So effectively what we want to know is this. If you increase global temperatures, how much does sea level rise? And how quickly? Is it going to be slow? Is it going to be a sort of not very sensitive to global warming? Is it going to be rapid? Are we going to get areas where the glaciers actually completely disappear? And so this curve looks like this. And so really, fundamentally, what we're trying to do is estimate this curve for those different ice sources, but also I'm going to bring in some other aspects as well. So the sources of our information here are going to be computer model simulations, and then on top of that, the machine learning to understand these uncertainties and get to probability distributions. So I'm going to start with, so I'm going to talk about the simulations first and the sort of concepts, and then get a bit more into the machine learning, and then actually end on some current work that we're doing as well to extend this. So thinking about the glaciers first, so you've got all these glaciers around the world, 200,000 or more, and here's one in New Zealand. And so we have a glacier model, will look like this. This is, the colours here are thickness of the ice. We've got these kind of troughs and branches coming in. And then this is driven by the output of a climate model, which has used emissions as an input. And so what we will typically have is perhaps simulations at different levels of global warming or different emission scenarios like this, perhaps 2, 3, 4, 5 degrees of warming, for the northern Canada glaciers, for tropical glaciers, and these relationships will look different for those different regions depending on how big the glaciers are, the local climate, the topography, and so forth. And so the simulations that we have used in this study that we did before the IPCC report for the glaciers come from a MIP, so a MIP being climate science jargon for a model into comparison project. So glacier MIP was using 11 different types of glacier model, driven by 10 different global climate models, which are a little bit similar to what we just heard about from Matthew. Under 4 different emission scenarios. These are called RCPs. These are old generation emission scenarios because that was what was available at the time. And then that, looking at all the different combinations, that was approaching 300 simulations, and that's for all of the glaciers. Although I'm just going to consider the 19 regions that I mentioned. So yeah, temperatures go up, sea level contribution goes up. And then for Greenland, basically, so the glaciers are the kind of simplest story, and then the ice sheets get progressively a bit more complicated. So for Greenland, we've got, it's sort of like a big glacier, sort of like a great big lump of ice up in the Arctic. This is an image of, over the last couple of decades, the thickness change that we've observed. And the blue in the middle is where, in a warming climate, we've got increased snowfall. So the ice sheet has actually thickened in the middle. But that's outweighed by what's happening at the edges in red, which is where the ice has melted because of the warmer climate over the last couple of decades. And so that's outweighing the gains. And so that's the snow and the melting. But what's different about Greenland compared with most of the glaciers is in all these fiddly fjords and troughs around the edge, quite often the ice sheet is reaching the ocean and is touching the ocean. And so these fjords, these troughs around this complicated coastline, the water comes in and can touch the ice, can melt it, can have a big influence on the ice, and you get these big icebergs carving off, breaking off. I think it was an iceberg from Greenland that sank the Titanic, actually. So that's a bit of history. So we need to think about not just the sort of atmospheric warming, which is how we typically think of global warming, but we've got to think about what the ocean is doing as well. Which means that we're going to now look at, for Greenland, 2 different relationships, not just the sensitivity to air temperatures, but also the sensitivity to ocean temperatures. So we're thinking about 2 relationships, and that bottom one is kind of encapsulated with a parameter, which they call the retreat parameter, the glacier retreat parameter, which effectively is governing the sensitivity of the glaciers retreating to ocean warming. There's a contribution from meltwater running off the ice sheet, but predominantly it's how much do the glaciers retreat as the ocean warms, and that's a parameter. I'm just giving a sort of overview of everything before we get to the machine learning bit. So here's a nice picture of a Greenland ice sheet model. This is finite element, actually. We had that term earlier called Elmer ice. It's just a really pretty graph of Greenland, I think. And again, we've got a MIP, a model into comparison project for ice sheets now. So for the Greenland part of ISMIP, we've got 14 different ice sheet models. We've got, they were forced by, again, 10 different climate models under 2 scenarios, pretty much. And what is helpful about Greenland, and we're going to come on to it for Antarctica as well, is that most of the models use this same retreat parameter that I just mentioned. So this kind of parameter that governs the influence of the ocean on the ice sheet. Unusually, most of the models use that same parameterization scheme. And that was effectively possible because it kind of sits at the border between the ice sheet and the ocean, sort of technically speaking. And so what that opens up to is thinking about how to describe multiple models and the uncertainty in their predictions in a common framework, because they are varying many of the same inputs. So we've got these two relationships I just mentioned of climate change and this retreat parameter. Just to show the multi-model average thickness change predicted, this is the kind of data that we're working with, although I'm just using the aggregated volume change of the whole ice sheet here. So that's the multi-model average thickness change in Greenland. So moving on to Antarctica quickly. So again, we've got a similar pattern of observed changes over the last couple of decades. We've got lots of snow happening around a lot of Antarctica, and that's a very important part of what's happening in Antarctica and very variable. But you can also see we've got in West Antarctica down here, this kind of armpit bit, we've got a lot of thinning of the ice. We've got a lot of ice loss there, actually some kind of sort of worrying bits starting here as well. And so Antarctica is even more dominated by ocean influence. So about 3/4 of it sits on bedrock that is touching the ocean. Most parts are touching the ocean, and that's particularly important for this. I just did the same thing about the slides. So the most of the West Antarctic sort of section here is sitting on bedrock underwater, and that makes it more vulnerable to ocean change. And actually I will show, you can see one sort of detail about Antarctica that is not always well known is there's a sort of black line here, which is all around the coast, and beyond that line are the floating ice shelves, which are fringing the ice sheet. So they are extending out over the ocean. And those are important because there are two different sort of potential triggers of Antarctica losing ice, losing mass. So there's the sort of direct ocean warming. So a bit like Greenland, the ocean is touching the ice in many places. And so this is a prediction for ocean warming around the Southern Ocean in the future. And the colours are red, it's going to get warmer. And so that's a way that Antarctica would lose more ice. But also ice shelves collapsing, which is down to the predominantly the atmospheric warming. You get kind of meltwater sort of accumulating on the ice shelf, it ends up breaking up the ice shelf. And if you lose an ice shelf, it was acting as a sort of buttressing to the glacier flow. And so you can end up basically with that glacier increasing the speed of putting ice into the ocean, and basically potentially even unstable behavior of the ice sheet. So, and that's also predicted, so these arrows are pointing to regions where the next ice shelves would be predicted to collapse under future warming. We've already seen a couple of collapses around the Antarctic Peninsula in the past, which is this bit up here. So that means we've now got three relationships to predict for Antarctica. We've got we're thinking about the overall sort of global warming emission scenario, we're thinking about the warming ocean, and we're thinking about the ice shelf collapse. And just like for Greenland, there's a sort of parameter that's dominating the sensitivity of the ice sheet to the ocean temperatures, which is called a basal melt parameter. So sensitivity to ocean temperature, and again, most of the models were using this particular parameter that sort of sits between, if you like, the ocean and the ice sheet. And then simulations basically were done under a scenario where lots of ice shelves were sort of collapsing in the future, or also without that collapse scenario. So that was kind of explored across different models as well. So just to show you an example of a nice Antarctic ice sheet model, this is one that my PhD students use called Bicycles. It's an adaptive mesh model, so you get finer resolution at the edge where most stuff is happening. And this is West Antarctica retreating under very extreme scenario, just to sort of illustrate it. So this is one of the models we have, but others have fixed grids and a few different properties as well, finite element. So for the ISMIP Antarctic part, similar sort of story. We've got about 14 different ice sheet models driven by lots of different climate models, again under about 2 emission scenarios, generating about 300 simulations. Again, here's some example results where you can see in the future we expect more loss from this West Antarctic area here and this East Antarctic area here. These are the ice shelves, so they don't contribute to sea level rise. And again, as I say, most of the models use this basal melt parameterization and this kind of common scenario of ice shelves collapsing or not applying that scenario. And so sort of focusing on the kind of warming relationship that I mentioned before for the glaciers or the ice sheets. Of course, the question here is, if we've got simulations under these 2 or 4 different scenarios, it gives us an idea of this picture, but an incomplete idea. So what we want to know is what this relationship looks like for any level of global temperature in the future, because we don't know what the future will be in terms of global warming. We want to know the exact shape of that relationship. If there's a plateauing here because all of the glaciers in that region are disappearing, what temperature might that occur at? It's very important for the people that live locally to those glaciers as well as for sea level rise. And so we want to explore this relationship in detail, and you can feel that this is where the machine learning is going to come in. So that was sort of warming, but we are also thinking about the dimensions of the model uncertainties that I mentioned, the parameters influencing their response. We want to be able to predict the sea level contribution in the future for any level of warming, as I mentioned, any values of the retreat parameter for Greenland, or the basal melt parameter for Antarctica, or whether the ice shelf collapse scenario is in place or not. And so what we are going to do is think about how to join the dots, how to interpolate and potentially slightly extrapolate, and think about the best way to do that. And so I'm just going to talk about old school Gaussian process emulation. And we like this because we want to be, hopefully this is, everyone who's come today will agree that we like to have an understanding of the uncertainties in our machine learning. And so that's why here I'm moving to Gaussian process emulation. So the emulation that we used here, we like Gaussian process emulation because it gives us uncertainty estimates. I'm sure most people are familiar with it. It's non-parametric. You're not putting in your own relationships, your own idea about what the physical relationship should be. Some people do use methods that are parametric, but I prefer Gaussian process, having sort of grown up in uncertainty quantification land. I'm just using an R package called RobustGauss that people might know, and predicting sea level contribution in each year independently. And that was just purely for practical reasons, not because we thought it was better. And the kind of key thing here that's different about most uses of Gaussian process emulation in this kind of context is the fact that we've got multiple models. And so typically in Gaussian process emulation, this is a really, if you don't know it, a really nice interactive demo webpage that I made these screenshots from. So you would have some model input, maybe it's the global warming, maybe it's the retreat parameter, and you've got some simulations of these dots along here, which are giving you the sea level contribution. And typically with Gaussian process emulation, as we saw in Sebastian's surrogate modeling talk, you would have the kind of mean function going through the dots, and then you would have the uncertainty intervals blowing up in between. But because I've got a multi-model ensemble, I'm treating it as a stochastic simulator, effectively, as noisy observations, like you would if you were doing kriging of real-world observations, if you had a stochastic simulator, this kind of thing. Because for each of these, for example, global warming levels, I've got a whole ensemble of models, 10, 15 different ice sheet models, for example. So I allow my Gaussian process to have that tolerance and not try to get through any particular dots by using a nugget term. And there's a judgment there that these models are independent enough, sufficiently independent to do that. And effectively, when these models are set up, when they're initialized, even the same model used by different groups, they end up with actually really different behavior. So we feel confident that they're independent enough to do this. And so what we have as a sort of how it looked in practice, as opposed to the conceptual diagrams, this is 4 of the 19 glacier regions. Now remember I said there was only one relationship to predict here, and that was just the relationship with global warming. So we've got the sea level contribution in the year 2100, just as an example, I am doing the whole time series, against the temperature change over the same period. And all of the dots are my glacier MIP simulations for the 4 different RCP scenarios, low warming to high warming, and then you've got the emulator mean and uncertainty intervals shown in grey. And you can see some of these glacier regions are indeed kind of disappearing, but mostly it's sort of fairly linear for these examples at least. For Greenland, we've got those two relationships I mentioned, global warming and the retreat parameter, the sensitivity to the ocean. And so here we've got, remember I said there were two scenarios, we've got a low emission scenario and a high, so low warming and high warming. Same idea, sea level contribution in the year 2100 against temperature change in the same period. Again, Greenland is a sort of big ice cube, it's like a big glacier, it's pretty linear in global temperature in the models. We've got these stacks of points from different global climate models here. You may be able to just about see, there's actually a second emulator envelope here, which is under a higher value of the retreat parameter, just to demonstrate that, which is what these open circles are as well. And then the other relationship, it happens to be an inverse relationship, the way that the parameter is designed. So this is this retreat parameter, and the more negative the retreat parameter, the more retreat you get for a given amount of ocean warming, effectively. So we've got a few different values of that in the simulations. This is just a subset of the ensemble to show a clean, design. But it wasn't a clean design, but a clean relationship. And again, so we've got that kind of fairly linear relationship there. And then I'll just show West Antarctica. I did Antarctica in 3 parts, West, East, and the peninsula. We've got actually not a very strong relationship with temperature here. It's quite noisy. These open circles, as I mentioned, are the higher value of the basal melt sensitivity, and there's again, you can't see, but there's a sort of a second emulator envelope for that. But they are strongly dependent on this basal melt sensitivity parameter. So we've got this kind of strong relationship here. And so then we want to, as Sebastian was talking about, we want to propagate all of our uncertain distributions on all of the inputs through our emulator. So we've got prior distributions on all of those things I've just mentioned. We've got distributions of global temperature change under different emission scenarios. And crucially, we've got lots of emission scenarios here, and they're modern emission scenarios rather than old ones or only 2. That was this key reason why we wanted to do things as a function of climate change. So these are all coming from a simple climate model, which is why they're big distributions of, rather than just a handful of global climate models. This is coming from a very fast, simple climate model. And then we've got those 2 parameters I mentioned. When the parameterizations were developed, then sort of empirical distributions were developed for those parameters. So certain values were considered more likely, basically. So we propagated those through. We've got ice shelf collapse scenario on or off, basically is just a binary. And then crucially, sampling from the GP emulator uncertainty as well, to make sure that that uncertainty is propagated through so that it's more robust and not underestimating the uncertainty. I'll leave you to read the paper if you want more details, but the sort of headline results, basically you add up all the ice sheets and glaciers and come up with projections for this century under different emission scenarios. This is basically just showing the whole thing. We did some sensitivity tests of kind of worst case scenario, or pessimistic scenario we called it up here, and showed the kind of relative difference we would make if we kept warming to 1.5 degrees of the Paris Agreement compared with the pledges that were made just before or while we were doing the analysis. So a halving of the loss of land ice. And this was very much a joint effort, a big team of 84 scientists across 15 countries, modelers, observationalists, statisticians, and all sorts. And then the way that we implemented that in the IPCC, so the IPCC isn't really doing new research, it's summarizing existing research and sometimes applying the methods that are published to perhaps new data sets. So we applied this to the latest IPCC projections of global warming. So we replaced these with updated projections for temperature. We combined it with the land ice with the ocean warming thermal expansion that I mentioned and the land water storage. And that's all within this nice probabilistic framework called FACTS, which you can look up if you're interested, to combine all of those different components and do all the bookkeeping to come up with this curve, which is basically to summarize what was new and what was the plan, the probabilistic sea level projections for multiple new generation emission scenarios using new projections of global warming and quantifying some ice sheet and glacier model uncertainties. So just to finish, I want to talk about, so that was a paper published in 2021, just before the IPCC report also came out in 2021. We're now working on a new analysis which we hope will fill some of the gaps of the last IPCC report and that study in particular. So I've talked to, it's impossible to avoid doing that, I think. So we've got on the left-hand side is what I've just been talking about, the 2100 projections, where we had this kind of, you know, this unique opportunity because most of the models had used the same retreat parameter and basal melt parameter. So we could emulate across all of the models at once and put them all into the same framework, the same emulator. And that was unique and relatively unusual, but it was still only, you know, 1 or 2 model uncertainties were being sampled and incorporated into the emulator. There was the simplification I talked about of predicting each year independently. So we effectively had probability distributions for each year, and that turned out to be problematic for people to interpret and use. And the simulations didn't start early enough for this all to be calibrated with observations. And you can ask me about why if you like, but basically it wasn't possible to calibrate the emulator projections with observations. And then if you look in the IPCC report, there are sea level numbers in the year 2300. There's not a time series, there's just a couple of bars here under the low emission scenario in blue and the high here in red, and this dotted line is a single study that goes off into very high numbers. But this is based on mostly, there aren't very many simulation studies that go out to the year 2300. You know, it's harder to find the climate models, to run the ice sheet and glacier models as long, particularly the climate models. And so a lot of what went into the literature here was some simple extrapolation, some expert elicitation, some sort of a little bit of modeling, physical modeling, but it's quite patchy evidence. A lot of it was older generation emission scenarios or even sort of quite abstracted scenarios. So these ranges were very much given low confidence. We had to kind of come up with something, but they're kind of relatively low information and confidence. So we're trying to address that gap, particularly the timescale of 2300. So I've been working for the last 4 or 5 years in an EU-funded project called Protect. 27 institutions across 9 countries funded with 10 million euros, and also roping in a few friends. I work a lot with the statistician John T. Ruger, the facts team that I mentioned of the sea level framework have been helping. And the idea of this project is to predict sea level rise predominantly from those land ice components in better ways than before, but also lots of coastal impacts predictions from those sea level rise numbers. Lots of talking to stakeholders. It's a big complex project, but this is one part of it. And what we have, so the project actually finished in February, so we're basically finishing the analyses and writing up the papers, but we've got many more simulations now to work with. So this is the previous MIPs were not funded projects, they were basically voluntary. This is a funded project. We've got the capacity to run many simulations in a slightly more designed way, slightly more control. So if we compare for the 3 land ice components, the IPCC, remember I said it was about 300 simulations for each. We're now getting into thousands, even to the year 2300. We've got 1,000, 2,000, 3,000 simulations for each. And those are exploring lots and lots more model uncertainties. So instead of just 1 or 2 parameters for the ice sheets, and nothing for the glaciers, remember, so that's this number here, 2 parameters, 1 parameter I talked about, none for the glaciers. We've got 24 for the Antarctic ice sheet and approaching 10 for the other 2. And these are of all types, so not just parameters like you know, continuous parameters, but different model resolutions are in there, different physical equations, parameterizations, initial conditions. We've got different regional climate models, which are higher resolution climate models at the poles to give better information. But the trade-off is we've got fewer models than the MIPS. We've got, you know, more like 3, 5 rather than 15, but we've been able to explore a lot more uncertainties for those models. So just to sort of say the kind of, if you're interested in hearing more about that, ask a question. But basically, the sort of the key thing that's difficult or hopefully an advance in that area is trying to put so many models and so many uncertainties into a common framework to emulate. So we're sort of translating between, what does a parameter in one model mean compared to the same parameter in another model? Do they have the same units, the same definitions? What do we put for, where we've got missing values, that parameter doesn't exist? And basically, just to cut a long story short, that involved a lot of conversations, a lot of conversations of trying to understand the model physics and how these models mapped onto each other so that we could put them in the same framework. So just to show you the aims that we are doing with this work, as I say, multi-model, multi-input Gaussian process simulation, including all of those model uncertainties I mentioned. I'm now doing a full-time series with principal components instead of independent years, longer time scale. We're able to calibrate with observations because the simulations start further back in the past, and that's what these are here. These are unpublished, but this is all the trends of the mass loss over the last 2, 3, 4 decades. And I'm also looking at sort of fancy GPs. So if you're using local LAGP or deep GPs, please come and find me in the break. So just to summarize, quantifying uncertainties and the land ice contribution to sea level rise to the year 2100 for the last IPCC report and 2300, hopefully, to inform the next. So Gaussian process of emulation of multi-model ensembles, including some or many of the model uncertainties, calibrating with observations in the next analysis. And the last thing I want to say is we're trying to make useful projections, but also have a postdoc starting soon. So please look out for an advert, or come talk to me or email me if you either are looking for a postdoc for a year or know anyone that is, and you can see my email address there. Thanks.
I have a question. So you had one slide where you don't need to find it, it's right, where you were comparing using a single GP to multiple GPs, and you were mentioning how the single GP usually is constrained to pass through the data points perfectly, and so on the multiple GPs maybe weren't in this instance. So I was just kind of curious how you were using multiple GPs, because if you add together the GPs, you just get another GP, which is kind of like a single GP with a composite kernel in some sense. And so I was, just curious to understand that a bit.
Yeah, no, I'm not using multiple GPs. I'm using a single GP to emulate the multi-model ensemble, so the multiple ice sheets all at once. So the emulator just sees lots of different simulations from different models all together in the same data set. So that was just an illustration to show the difference between using one versus emulating one model versus emulating an ensemble of models, but I'm only using one GP. Yeah.
And I guess related to that, have you looked at trying to learn the covariance function and possibly, interpret what it might be saying about this problem?
Not learning it, but I think the interpretation is a key part of checking whether the covariance functions look sensible, is looking at the relationships that come out and are they what we expect, typically kind of monotonic, a lot of them tend to be sort of generally increasing or plateauing, or there are various shapes of these relationships that you would think smelt wrong. So it's more the other way around. I think the physics knowledge informs what the realistic covariance functions would be. Yeah.
Any other questions? Yeah.
So in Matthew's talk, I guess, he talked about moving away from physics-based models more to data-driven things. Whereas here, it's all kind of primarily physics-based. Will there come a point soon where we have sufficient observations of ice sheets to have a more kind of data-driven approach?
Well, obviously the big difference between weather and climate is how much the climate is changing under these uncertain future boundary conditions. So, I mean, I think you would... I think, in a way, the sort of emulating as a function of climate is supposed to be accessing that. So you could imagine, maybe using... if you had simulations going back further, and so you had a longer lever of climate change, and you could maybe start to map this out. But I think if you were kind of trying to extrapolate into the future, maybe under even more warming or different shapes of emission scenarios, you need to know the physics. We know so little, for example, about what Antarctica will do in response to a climate change that goes up and then goes back down. If we manage to reverse climate change with carbon dioxide removal, which some people think you can and some people emphatically think you can't, does it induce a tipping point? Does it induce irreversible change? and you absolutely need physics for that, and we don't have enough knowledge in that area yet. Maybe maybe there is some golden future where we know all of the physics and have mapped that out enough to not need them, but it would be a few years off yet.
All right, thank you.